Geometry, Chapter 5, Section 3, Bisectors and Triangles. This first part, we're going to talk about perpendicular bisectors. So first, what we need to do is give an example. We need to construct a circle and label the center C, as in the example of the right. Choose any 3 points on the line and connect them to form a triangle. Draw the 3 lines from C such that each line is perpendicular to one side of the triangle. So we're going to draw a line there, there, and again, using our compass, we could do this a little bit better. There. Okay. What conjecture can you make about the 2 segments in which each side of the triangle is divided? All right. Let's look at this. So from the circle we made and the center, what do we know about the center to the edge? That's called the radius. And we know from each vertex of the triangle to that C spot, those 3 lines are all congruent to each other. So right now what we know is if we can find what looks like perpendicular bisectors, they're going to intersect or all merge at a point of concurrency. That means where all 3 points go. All right? And we call this spot that we circumscribed right there the circumcenter. The reason it's got that name, where all points of those 3 perpendicular bisectors go, why we call that the circumcenter, is because the circle surrounds the triangle. All right? The triangle is inside the circle, so the circle circumscribes the triangle. So this is called the circumcenter. All right. So let's go talk about what we just shown on that last slide. For any triangle, certain sets of lines are always concurrent. Again, that means 3 lines all intersect the same spot. One set includes the perpendicular bisectors of the triangle's 3 sides. So here's our theorem. The perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So here's the diagram. So you can see X is the midpoint of AB, Y is the midpoint of AC, and Z is the midpoint of BC. So we extended a line perpendicular from point X out. We extended a line from point Y perpendicular to AC, and we extended a line from point Z perpendicular to BC. And they're all going to intersect at point P. That's where they're all concurrent. So when we do that, we know PB is going to be congruent to AP, which is going to be congruent to PC. Okay, again, where all the perpendicular bisectors intersect to the point of concurrency, and that point of concurrency is called the circumcenter. Okay, the point of congruency of the perpendicular bisector we just said is the circumcenter of the triangle. Since the circumcenter is equidistant from the vertices, you can use the circumcenter as the center of the circle that contains each vertex of the triangle. You say that the circle is circumscribed about the triangle. Okay, and we've done that before. So the circumcenter of a triangle can be inside the triangle, outside the triangle, or on the triangle. If it's an acute angle triangle, all the angles are small, it's less than 90, it's going to be inside the triangle. If you have a right triangle, the circumcenter is always going to be the midpoint of the vertex. Always going to be the midpoint of the vertex. If you have an obtuse triangle, meaning one of the angles is greater than 90, it's going to be outside the triangle. All right. So finding the circumcenter. What are the coordinates of the circumcenter of a triangle with vertices of 0, 6? So we plot 0, 6, 0, 0, and 4, 0. Well, what do we notice right now? We notice this is a right triangle. So we know, without having to do too much, we know the circumcenter is going to be the midpoint of PS. So how do we find the midpoint of PS? So how do we find the midpoint of segment PS? All right, well, we're just going to add the x of P plus the x of S, divide it by 2. That'll give us our x midpoint. Y of P plus y of S, and divide that by 2. So the x of P is 0. The x of S is 4. So 0 plus 4 over 2 is 2. The y of P is 6. The y of S is 0. So 6 over 2 is 3. So the midpoint of this is 2, 3. That is also the circumcenter. All right. We could have also went about a different way, and we could have found the perpendicular bisectors of each line, which would have given us the exact same answer. All right. What are the coordinates of a circumcenter of a triangle with vertices of 2, 7, 10, 7, and 10, 3? Well, just by looking and reading the points, we know this is going to be a right triangle. So 2, 7, so 1, 2, 1, 2, 3, 4, 5, 6, 7. So there's point A. 10, 7. So there's point B, and 10, 3. And there's point C. So we can draw our triangle. I'll do the best I can to draw it properly. So there we go. Well, we notice we have a vertical line and a horizontal line, so we know that's a right triangle. So based on the rules of right triangles, we know the circumcenter is going to be the midpoint of this segment. So A was 2, 7, B was 10, 7, and C was 10, 3. So we need to find the midpoint of the hypotenuse, which is AC. Okay, so it's going to be the x of A plus the x of C over 2, the y of A plus the y of C over 2. The x of A is 2, the x of C is 10, so 2 plus 10 divided by 2, 12 divided by 2 is 6. Okay, the y of A is 7, the y of C is 3, so that's 7 plus 3, it's 10, divided by 2 is 5. So the midpoint of AC is 6, 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So that's the midpoint right there. That is also the circumcenter. Okay? Using the circumcenter. A town planner wants to locate a new fire station equidistant from the elementary, middle school, and the high school. Where should he locate the station? Okay. Well, the three schools form a vertex of a triangle. So let's look at this. So I want to do it equidistant from the high school, the elementary, and middle school. So let's draw a line. Let's draw our triangle. There we go. Now I'm just going to freehand this, but we would find the midpoint of each one. And we would go perpendicular. So just a quick sketch, that's probably close to being perpendicular. That's probably close to being perpendicular. And that's close to being perpendicular. So it's close to being a right triangle. So somewhere in that point right there is going to be the circumcenter. Okay, obviously we could do a little bit better to actually find it. But for the sketch, that's close enough for us. All right, so we see that we can find the circumcenter just by plotting the perpendicular bisectors. All right, so in problem 2, the town planner wants to place a bench equidistant from the trees in the park. Where should he place the bench? Okay, so let's draw our triangle. And again, we're just going to take a shot here. That's about the midpoint. Again, we could get the compass out and really do this right. There's a right triangle. So there's the midpoint. And there's the midpoint. Again, they all line up right there. We'll mark it. There's the point for our bench. Again, what do we know about that bench? we know that bench is going to be equidistant from point A, point C, and point B. All right. That kind of concludes perpendicular bisectors. Now let's talk about angle bisectors. So the last example, we drew a circle outside the triangle, which circumscribed it. Now let's do a circle inside the triangle, or that's inscribed. Okay, and where those points meet, we will line up perpendicular, not bisectors, but perpendicular lines to each side. That point of concurrency right there is called the incenter of the triangle. And what do we know about the incenter? We know that's where all the angles or the angle bisectors intersect of a triangle. So this will always be inside the triangle. And the point for the incenter is always equidistant to each side. Okay? So it's equidistant each side. So let's talk about this. The concurrency of angle bisector. The bisectors of angles of a triangle are all concurrent at a point equidistant from each side. So the angle bisectors here, AP, BP, and CP, are all concurrent at point P. And what do we know is PX is congruent to PY is congruent to PZ. So how can we tie all this in together? All right, so let's look. It tells us segment EG has an equation of 2x minus 7, and GF has an equation length of x plus 4. Since G is the point of concurrency of the triangle of all the angle bisectors, we know those two segments, since they're perpendicular to opposite sides, are equal. So we can just say 2x minus 7 equals x plus 4. Subtract x to each side, so I get x minus 7 equals 4. Add 7 to each side, so x equals 11. All right, but it didn't ask for what x was, it asked for what GD is. So let's plug x back in for 11. So 11 plus 4 equals GD. So 11 plus 4 is 15. So segment GD is 15 units. Okay? Moving on to the next example. All right, QN is 5x plus 36. That's QN. QM is 2x plus 51. Well, we know point Q is the incenter because it's the intersection of two angle bisectors of the triangle. So we know segment QN is congruent to QM. So we can say 5x plus 36 is equal to 2x plus 51. So we're going to subtract 2x to each side. So I'm going to get 3x plus 36 equals 51. Subtract 36 to each side, so I'm going to get 3x equals 15. Divide each side by 3, x equals 5. All right, so x equals 5. So QO is going to be the same thing, so we just got to plug it back in. So 2x, or 2 times 5 plus 51 equals QO. We know that because we can use either equation. So QO is equal to 61, which means QN is equal to 61, which means QM is equal to 61. All right. Is it possible for QP to equal 50? Is it possible for QP to equal 50? Well, QN equals 51. Equals 61, and it is the shortest distance between a point and the side, that segment. So there is no way QP could be less than 61. So the answer would be no. And what is QO? We already said that is 61. And the answer is it possible for QB to equal 50? The answer is no, because QN is shortest possible. So QP must be greater than QN. Okay, moving on. In the figure below, TV equals 3x minus 12 and TU equals 5x minus 24. Solve this out and pause it here. All right, now that you've checked your work, you can see what we did. We set TV equal to TU, and we got X equals 6.